welcome to the 9th session of probability. In the previous class, we finished off with problems on Bayes' theorem. In today's class, we will start off with a new topic, that is random variables and their probability distribution. As the name itself says, there are two concepts here. The first concept is that of random variable. Then we will see what is probability distribution. Now, the definition of random variables goes like this. Random variable is a function. It's a real valued function whose domain is the sample space of an experiment. I repeat the definition once again. A random variable is a real valued function whose domain is the sample space of a random experiment. Now, in that definition, there are two parts there. One concept is, it is saying it is a real valued function. What is the meaning of a real valued function? A function whose codomain is the set of real numbers is called a real valued function. Or in other words, in simple words, the values of the function must be real numbers. But then, what is the domain of the function? In the definition, it is saying domain of the function is the sample space of a random experiment. To illustrate that definition, we will use an example. Say, I consider the experiment of tossing two coins. So the experiment we are considering is tossing two coins. Okay? What is the sample space of this experiment? As we all know, we have totally 4 different elements in the sample space. Which are they? HH, HT, TH and TT. So the sample space, if I denote it by capital letter S, set as equals, if I am denoting capital H, heads by capital H, tails by capital letter T, then sample space becomes HH, comma, HT, comma, TH, comma, TT. So there are 4 different elements in the sample space. Now, I will define a function. Say, name of the function is capital X. So the name of the function is capital X. Let this function X denote number of heads. Number of heads. Okay? So what have we done? We have taken a random experiment. The random experiment is tossing two coins. Sample space has 4 different elements. We have written the sample space. And what is capital X? Capital X is a function defined on sample space S. What is the definition of function X? It is number of heads. Definition of X is number of heads. Okay. Now, what is X of H? Since X is a function on capital S, okay, each element of the set S will have a value under X. We are going to find out that value. So, X of HH, what is that equal to? What is X? X denotes number of heads. How many heads are there in HH? There are 2 heads. So, value of X, value of HH under X will be 2. So, I can write that as X of HH equals 2. Then, value of HT, that is X of HT. How many heads in HT? 1 head. So, I can write that as equal to 1. Then, X of TH. X of TH. How many heads in TH? 1 head. That is equal to 1 again. Last one, x of tt. How many heads are there in the outcome tt? No heads, 0 heads. So value of tt under x will be equal to 0. So we have got 4 different values of x. X of hh is equal to 2, x of ht is equal to 1, x of th is again it is equal to 1, and x of tt it is equal to 0. Now we can clearly see that, okay, according to the definition of random variable, we must have a real valued function. In this case, look at values of x. These are the values of x. Which are the values of x? 0, 1, 1 and 2. Are all these values real numbers? Yes. So I can say x is a real valued function since all values of x, okay, are real numbers. 0, 1 and 2 are real numbers, hence x is a real valued function. Then is x a function defined on set S, the sample space? Yes, we have defined x on the sample space S. Hence, by the definition of random variable, we can conclude that capital letter X is a random variable. So once again, repeating the definition of random variable. What is the definition of random variable? A random variable is a real valued function whose domain is sample space S. So I have given an example. We have taken the random experiment of tossing 2 coins. We wrote its sample space. Then we defined a function, a real valued function, capital X, on the sample space S. So this X can be called a random variable. So that is about random variable. Then moving on, the other concept is that of probability distribution. In full, it is actually probability distribution of a random variable. We will continue with the same example. To understand what probability distribution is, okay, we have got a random variable capital X. X denotes number of heads. X is denoting number of heads. Now, what are the possible values that X can take here? X can take the values 0, 1 and 2. Only 3 possible values X is taking. Either X can take the value 0, or it can take the value 1, or it can take the value 2. I'll write that here. The possible values of capital letter X are 0, 1 and 2. Okay. So there are 3 possible values that the random variable capital X can take. Now we have to think, can we find out the probability when X takes the value 0, when X takes the value 1, when X takes the value 2, okay? We are finding out what? Probabilities when X takes the value 0, when value of X is 1, when value of X is 0, when value of X is 2, okay? So I will denote probability when X takes the value 0 as capital P of capital X equals 0, okay? We are thinking about finding out the probabilities when X takes the value 0, when X takes the value 1 and when X takes the value 2. Probability of X taking the value 0, I have denoted it like this, capital P of capital X equals 0. Okay, now look at this. When will X take the value 0? Look here, when is X taking the value 0? Here, X of tt equals 0. So when we are having 2 tails, value of x will be 0 when we are having 2 tails. So in this experiment of tossing 2 coins, we must be getting 2 tails. When we get 2 tails, then value of x will be 0. So I can write P of x equals 0 equals probability of getting 2 tails, right? Because x takes the value 0 when we have 2 tails. So I can equate P of x equals 0 to P of t. Now, what is probability of the event tt? Totally we have 4 elements in the sample space. One of them is tt. Hence, probability of getting the outcome tt is nothing but 1 by 4. So, probability of getting the outcome tt equals 1 by 4. Hence, I can say probability of x taking the value 0 is nothing but 1 by 4. Similarly, probability when x takes the value 1. What is the probability when x takes the value 1? Well, look here. When will x take the value 1? When we either have ht or th. So I can basically write here P of ht comma th. Probability when x equals 1 is nothing but probability of the event wherein we get ht or th. Now, how many elements are there in that event? We have 2 elements. How many total elements in the sample space? 4 elements. So what is the probability of this event? It is nothing but 2 by 4. On further simplifying, we get this to be 1 by 2. Hence, probability when x equals 1 is 1 by 2. Last one. Probability when x equals 2. When is x taking the value 2? When we have the outcome HH, probability x takes the value 2. Hence, probability of x equals 2, I can write it as probability of getting the outcome HH. So what is probability of getting the outcome HH? It is again 1 by 4. So we have found out the probabilities when x takes the value 0, 1 and 2. Now, if I can write this idea in a tabular column, okay, in a tabular form, wherein in the first row I will write the possible values that x can take, and in the second row I will write the corresponding probabilities when those possible values are occurring. Okay, so for example, in the first row I write capital X. What are the possible values that x can take? 0, 1 and 2. So that is 0, 1 and 2. Okay, so this is first row. In the second row, what do I write? I write down the corresponding probabilities. So I will denote this as P of x. So when x takes the value 0, what is P of x? Probability of x is 1 by 4. So I write it here, 1 by 4. When x takes the value 1, what is the corresponding probability? It is 1 by 2. So I write here 1 by 2. When x takes the value, what is the probability? It is 1 by 4 again. So I write 1 by 4. So what have we done? I have taken a random variable, found out its different possible values, also found out the corresponding probabilities, and that I have just written it in a tabular column, where in the first row we have the different possible values of x, and in the second row the corresponding probabilities of x. This table, this system of numbers is called the probability distribution of the random variable x. Okay, one more thing you need to notice. Okay, here in the second row, we have the probabilities of different values of x. Every number is in between 0 and 1. 1 by 4 is a number which is in between 0 and 1. 1 by 2, it is 0.5. It's a number in between 0 and 1. Again we have 1 by 4. 1 by 4 is nothing but 0.25. Again that is the number in between 0 and 1. So every probability must be a number in between 0 and 1. It cannot be anything other than that. The second point is when we add the probabilities, okay? For example, what are the probabilities here? 1 by 4, 1 by 2, 1 by 4. If I add all three probabilities, what do we have? 1 by 4 plus 1 by 2 plus 1 by 4. 1 by 4 plus 1 by 4 is 1 by 2. Half plus half gives us 1. So we see that adding all the probabilities must give us the value 1. So 2 points. First point is every probability must be a number in between 0 and 1. Okay? And the second condition is when you add all the probabilities, they must add up to the number 1. So in light of this illustration, I will just give you the definition of probability distribution. Probability distribution of a random variable is the system of numbers. So in general, I can write the system of numbers x in the first row. This is nothing but the possible values of random variable. I can take it as x1, x2 up to say some finite number xn. Then p of x in the second row, that is corresponding probabilities of different values of x. I can denote it by small p1, small p2, so on up to small pn. Okay? So we are going through the definition of probability distribution. Probability distribution of a random variable capital X is the system of numbers like this, which looks like this, a tabular column. Okay? The only conditions on this is nothing but every probabilities, that is numbers in the second row, must be numbers in between 0 and 1. So I can write 0 less than pi less than 1. This is condition number 1. 0 less than pi less than 1 for all I. What is the meaning of this? This simply means that every probability is a number between 0 and 1. That is all this means. I showed you here 1 by 4, 1 by 2, 1 by 4. All three numbers are numbers in between 0 and 1. So that is what this first condition is telling us. And the second condition is what? When you add all the probabilities, it must add up to the number 1. So here, which are the probabilities? How have we denoted those numbers? P1, P2 up to Pn. So I will write P1 plus P2 plus so on plus Pn must be equal to 1. Or compactly writing in sigma notation, how can I write the LHS? I will write sigma I equals 1 to n Pi must be equal to 1. So when you add all the probabilities, it must add up to number 1. So this is about random variables and probability distribution. We shall move on to problems now. Look at the first problem. Problem number 1 states that let capital X denote the number of hours you study during a randomly selected school day. Next sentence, the probability that capital X can take the values small x has the following form where k is some constant. Now they have defined the random variable probability distribution like this. P of capital X equals 0.1 when X takes the value 0. So what is this telling us? When the random variable capital X takes the value 0, its probability, corresponding probability is 0.1. When X takes the value 1 or 2, random variable X takes the value 1 or 2, then its corresponding probability is Kx. What is K? K is some constant. Then when X is 3 or 4, what is the corresponding probability? It is K into 5 minus X. And if it is any other number other than 0, 1, 2, 3 or 4, it is corresponding probability is 0. That is why they have written 0 otherwise. What is the question asking us to do? We have to find the value of the constant K. Okay, first and foremost, we will write this probability distribution in the tabular form, just like we wrote during when I explained the definition. Okay, so we start the solution like this. The probability distribution of X, capital X, random variable X is, I can write capital X in first row. So what are the different values that X can take? 0, 1, 2, 3 and 4. So I write that in the first row. Start from 0, 1, 2, 3 and 4. Then corresponding probabilities of different possible values of X. I'll write that as P of X. What are the corresponding probabilities? When X is 0, what is the probability? It is 0.1. When X is 1 or 2, when X is 1, value is K into X. So that is K into 1, which is nothing but K. I repeat once again, when X is 1, value of probability is K into X. So when X is 1, what will K into X become? It becomes K. So it is K here. Then when X is 2, again the value is Kx. When X is 2, this becomes K into 2. It is 2K. It is 2K. Again, when X is 3, we have to consider this equation, this expression, K into 5 minus X. When X is 3, we have what? 5 minus 3 is 2. 2 into K. So I'll write it here. When X is 3, okay, we have to use K into 5 minus X. So that is K into 5 minus 3, because X value is 3. So 5 minus 3 is 2. 2 into K is 2K. So when X is 3, I have to write 2K again. Okay. When X is 4, again I'll have to take the same expression, K into 5 minus X. What is that? K into 5 minus X is K into 5 minus 4. 5 minus 4 value is 1. 1 into K is K. So I have to write K here. So I have written the probability distribution in tabular form, wherein the first row we have written the different possible values that random variable X can take. Which are the possible values? 0, 1, 2, 3 and 4. Then the corresponding probabilities. What are the corresponding probabilities? 0.1, K, 2K, 2K again and K in the end. So we have written the probability distribution of the random variable capital X. But what is the question asking us to do? The question is asking us to find out value of K. I told you there are two conditions in probability distribution. The first condition is what? Every probability must be a number in between 0 and 1. Can we use that condition here? No. If we use that, we cannot find out the value of K. Our aim is to find out value of k. Look at the second condition. What is the second condition? When you add up the probabilities must add up to 1, right? So we can use that condition to find out value of k. We will use that condition. What is condition number 2? When you add the probabilities must add up to number 1. So adding all the probabilities, 0.1 plus k plus 2k plus 2k plus k. So I'll start like this. We know that sigma pi, when I takes the value from 1, 0 to 4, because here we have 0 to 4, I will take I as taking the value from 0 to 4, it is equal to number 1. So when x takes the value, or I can write this as px, okay, so x taking the value 0 to 4, when x takes the value 0 to 4, p of x is equal to 1. So what is this? LHS is nothing but, what are the different probabilities? 0.1 plus k plus 2k plus 2k plus k equals 1, right? When you add all the probabilities, it must add up to the number 1. So we add this, what do we get? 0.1 plus k plus 2k plus 2k plus k gives us 6k equals 1. I will take 0.1 on that side. What do I get? 6k equals 1 minus 0.1. 1 minus 0.1 is 0.9. 1 minus 0.1 is 0.9. 0.9 I can write it as 9 by 10. Okay. So simplifying this, 3 2s are 6, 3 3s are 9. Okay. So what is value of k? Value of k is nothing but 3 by 2 10s are 20. So value of k, we found it out to be 3 by 20. So whenever probability distribution is given, you have to think about two conditions. The first condition is all the probabilities must be numbers in between 0 and 1. See whether that using that you can find out what the question is asking you to do or not. If you cannot find out, then use the second condition. What is the second condition? Adding all the probabilities, it must add up to the number 1. So in this case, the first condition was not useful for us to finding out the value of k. So we use the second condition, which is adding all the probabilities so that it adds up to 1. So using that, we have found out the value of k to be 3 by 20. Moving on to second problem. Problem number 2 states that state which of the following are not probability distributions of a random variable. Give reasons for your answer. So we have 4 sub-questions here. 4 probability distributions are given here. So what is the question asking us to do? We have to check whether these tabular columns represent probability distributions of a random variable or not. So just like the previous problem, the first we are going to use the 2 conditions of probability distribution. What is the first condition? Every number in the second row, that is every probability must be a number between 0 and 1, and adding all the probabilities, it must add up to the number 1. If both the conditions satisfy for each system of numbers, only then we will say that particular system of numbers represents a probability distribution of a random variable. Okay, look at the first sub-question. Sub-question 1, we have the probability distribution, we have the system of numbers. In the first row, x, 0, 1, 2, those are the possible values of x. In the second row, p of x, 0.4, 0.4, 0.2. So what is the first condition? We have to look at the probabilities. Are the probabilities all numbers in between 0 and 1? Well, 0.4 is the number in between 0 and 1. 0.4. Again, 0.2 is also a number in between 0 and 1. So, first condition satisfied. I can write, we see that Pi, or I can write 0 less than Pi less than 1 for all I. Okay, this is condition number 1. Why have I written this? What is the meaning of this? Pi represents these numbers in the second row. Okay, so every Pi is in between 0 and 1. 0.4 is in between 0 and 1. 0.4 again. 0.2 is again in between 0 and 1. So I have written 0 less than P1 less than 1. Pi less than 1 for all I. So that is condition number 1. What is condition number 2? When I add all the probabilities, it must add up to number 1. Well, let's check that. We have, what is that? 0.4 plus 0.4 plus 0.2. What do we get? 0.4 plus 0.4 is 0.8. 0.8 plus 0.2, we get it to be 1. So we can see that both conditions of probability distributions are satisfied by this system of numbers. Hence, this system of numbers is a probability distribution. So we have to give reasons for our answer. So the reason we have given here, first condition is every probability is in between 0 and 1. Second condition is when we add all the probabilities, it adds up to the number 1. So hence I can write the system of numbers is a probability distribution. Okay, so the system of numbers in sub-question 1 is a probability distribution. Similarly, we have to check for the remaining 3. We'll see the second sub-question, sub-question number 2. Okay, what are the probabilities? We have 0.1, 0.5, 0.2, minus 0.1 and 0.3. What is the first condition of probability distribution? All numbers in the second row must be numbers in between 0 and 1. But what can we see here? There is a negative number. When x takes the value 3, what is the corresponding probability? It is given to be minus 0.1. But minus 0.1 is not a number in between 0 and 1. Hence, the first condition for a probability distribution itself does not hold. So, hence, this system of numbers in sub-question 2 is not a probability distribution. So, what is the reason? Since, I can write, since minus 0.1 does not belong to, I can write, does not belong to open interval 0, 1. Does not belong to open interval 0, 1 means it is not a number in between 0 and 1, right? So I can write minus 0.1 does not belong to open interval 0, 1. The system of numbers is not a probability distribution. The system of numbers is not a probability distribution. What is the reason? Because minus 0.1 is not a number which is in between 0 and 1. So the first condition of probability distribution is not holding. That is why this system of numbers is not a probability distribution. Moving forward, look at sub-question number 3. We have 0.6, 0.1, 0.2. Okay. So are all these numbers in between 0 and 1? Yes. So first condition for probability satisfies. What is the second condition? We have to add all three probabilities and see whether it adds up to 1. 0.6 plus 0.1 is 0.7. 0.7 plus 0.2 gives us 0.9. 0.9 is not equal to 1. Hence the second condition does not hold. Hence what can we conclude? This system of numbers is not a probability distribution. So what is the reason? Is sub-question number 3. I will write, since 0.6 plus 0.1 plus 0.2, what did we get? We got 0.9 not equal to 1. This system of numbers is not a probability distribution. This system, which system? System in the third sub-question. It's not a probability distribution. Okay, last one, fourth one. Okay, what is given there? What are the numbers in probability in row 2? 0.3, 0.2, 0.4, 0.1, 0.05. So condition number 1, all the numbers are numbers in between 0 and 1. But what about the sum of the numbers? 0.3 plus 0.2 gives us 0.5. 0.5 plus 0.4 is 0.9. 0.9 plus 0.1 is 1. 1 plus 0.05 is 1.05. So you can see that the sum of all the numbers in row number 2 is more than 1, or it's not equal to 1. Hence again, that system of numbers in sub-question 4 cannot represent a probability distribution. So what is the reason? Similar to sub-question 3, since 0.3 plus 0.2 plus 0.4 plus 0.1 plus 0.05, we got it to be 1.05 not equal to 1. What can I conclude? This system is not a probability distribution. Okay, so what have we come across in today's class? I discussed about probability distribution. So you remember that whenever you have a problem on probability distribution, we are thinking of two conditions. First condition is every number in the second row must be a number in between 0 and 1, and the second condition is when you add all the numbers, they have to add up to the number 1. So if both the conditions are satisfied, then that system of numbers will be considered a probability distribution. If not, you cannot consider that as a probability distribution. Okay, that's it for today's class. We'll meet in the next class. Thank you.